Hello. Streaming data is everywhere, and its growth seems unstoppable. Activity from social networks, website analytics, and sensors and IoT devices generates a constant flow of new data coming at us from a huge number of sources. In this video, we'll see how Redis can help us capture, manage, and make sense of these large and constantly moving volumes of data right out of the box. Streaming data is data that's generated continuously, often from a large number of concurrent sources. One useful way of thinking about a stream is as a series of events. Every entry in the stream represents a new event. For example, you can imagine recording a stream of weather sensor readings at a given location. Every entry in the stream might consist of a temperature, a humidity measurement, and the wind direction and speed. Because streams and events are such a useful abstraction and occur so often in the real world, Redis provides a data structure called a stream. In the rest of this video, I'm going to introduce some streaming concepts, and then I'll demonstrate some of the basic commands you can use to manipulate streams in Redis. So let's start with concepts. In a distributed application architecture, the components that write to a stream are called producers. The data they generate is added to a stream, with each entry having a unique identifier and its specific fields. At the other end of the stream are one or more consumers. These consumer processes read entries from the stream and process them as necessary. What's interesting is that you can have more than one consumer reading from your stream. Each consumer has its own role. For example, one type of consumer might create notifications in a mobile application when certain trigger values are seen in the data. Another consumer might write all entries to a data warehouse for later analysis, while a third consumer could act as a producer for yet another stream, adding only a subset of the entries to the new stream. Producers and consumers often operate at different rates. The stream acts as a buffer between them, as well as a decoupling mechanism. This means that producers and consumers don't directly communicate with each other, so don't need to know anything about each other's implementations. Now let's talk about the Redis stream data structure itself. A Redis stream is a data structure that behaves like an append-only log. Once added, an entry in a stream is immutable. Each entry in a Redis stream has a unique ID, and by default, these IDs are timestamp prefixed. This means that a Redis stream keeps entries ordered as a time series. Stream entries look a lot like a Redis hash. Each is a set of name-value pairs. It's also worth noting that Redis streams are schemaless. While each stream entry has to have at least one name-value pair, they don't all have to use the same structure. Redis allows consumers to read stream entries in order. Consumers can also efficiently seek to any entry within the stream. So enough theory. Let's look at Redis streams in action. We'll see how they fit into a common use case for streaming data systems, recording real-time crowdsourced data. Imagine we're building a mobile app that allows users to check in at all sorts of businesses, public spaces, and workplaces. Users provide star ratings based on their experience at each location. Each time a user checks in, they'll pick out their location from a list our app provides. They'll then select a star rating from 0 to 5, and the app will send this data along with their user ID to a server. Users earn prize draw entries for each check-in, and we periodically offer cool prizes to randomly drawn winners. This incentive encourages users to check in often, improving their chance of winning. A typical check-in can be represented as a set of name-value pairs. Here we have a check-in for user ID 99 at venue ID 103. The user decided to give this venue 4 stars. Readings from our many users are sent continuously to our servers, and those servers produce entries into our Redis stream. Once this fire hose of jumbled data is added to a Redis stream, we can begin to organize and make sense of it. Let's see how each check-in finds its way into a Redis stream. First, like other Redis data structures, a stream is associated with a Redis key. We'll use the key check-ins to identify the incoming stream of check-in data. The xadd command adds a new entry to a stream. Here, we're adding an entry to the check-in stream from user 90781. This user is visiting location 348 and rating it 3 stars. The asterisk in the xadd command tells Redis to assign this entry a unique ID consisting of the current timestamp plus a sequence number. Xadd returns the ID that Redis has assigned to the new entry. The first part is the timestamp in milliseconds, and the second is a sequence number. Since stream IDs must be unique, this convention ensures that we can add as many entries as we need in the same millisecond. Now that we have check-ins flooding into our stream, it's time to think about how the business can make sense of them. As Redis assigns each entry a timestamp-based ID, one way that a consumer can view the stream is as a time series. Here, we're using the xrange command to read entries in the check-in stream that fall between the specified start and end timestamps. Xrange returns each entry whose ID falls within the specified time period. Entries are returned in order, with the oldest first. To limit the number of entries returned, we can use the optional count modifier. If we want the most recent entries first, we can use the xrevRange command instead. Note that here, we specify the time period in the reverse order, with the end timestamp coming first. And if we don't know what time period the entries in the stream cover, we can use both xrange and xrevrange with a special plus and minus operators to represent the highest and lowest timestamps respectively. Here we're retrieving the oldest two entries in the stream. But really, streams are all about real-time data consumption. So we want to build consumers that continuously receive data. We could achieve this by pulling the stream using the xrange command, but that's inefficient. Ideally, we want a command that lets us consume the stream, blocking when we've seen all the entries until a producer adds new ones. This is one of the use cases for the xread command. Xread can consume one or more streams, optionally blocking until new entries appear. Here, I'm calling xread against the check-in stream. Xread consumes the stream, returning entries whose IDs are greater than the one provided. Here, I'm asking for all entries with an ID greater than 0, the beginning of the stream. And Redis returns the entire stream. We'll need to note the ID of the latest entry for subsequent calls to xread. We can also invoke xread in a way that blocks the consumer until new entries are added to the stream. To use xread in a blocking context, I'll provide the last entry ID from my previous call. I'll also specify I want to consume a single new entry, and how long to block in case the stream doesn't yet contain any entries newer than the one whose ID I'm supplying. Here, I'm telling xread to block for up to 5,000 milliseconds or 5 seconds. When I run this command, it blocks because no new messages with higher IDs than the one I provided have yet been added to the stream. While the consumer is blocked, I'll use a second Redis CLI session to add a new entry to the stream. As soon as I do that, the consumer unblocks and xread returns the newly added entry. If no new entries have been added in a 5-second blocking period, xread would have returned a nil response. I could then choose to block again or give up trying and do something else. It's important to note that consuming the stream using xrange, xrevrange, and xread doesn't remove entries as they are retrieved. Entries remain in the stream, allowing other consumers to read the entire dataset, each processing it in its own way. Here, one consumer is maintaining running average star ratings. A second writes the entries to a data warehouse, and a third adds entries to another stream if the star rating is below a triggered threshold. So if new check-ins are constantly pouring into our stream, and consumers reading them aren't removing them, then how do we contain this seemingly never-ending growth? Remember that a stream models an append-only log. This means that the order and content of entries can't be modified once they've been added. However, Redis supports a trimming strategy to manage a stream's memory use. Let's assume our stream now contains tens of thousands of entries and that we need to control its growth. Trimming a stream removes its oldest entries, that is, those at the lowest timestamp IDs. This frees up memory associated with these entries. Let's see how that works in practice. Redis commands can be used to trim a stream. The first of these is xtrim. This command can be run at any time and trims the stream's length to a specified new length. Here we're using xtrim to trim our check-in stream to a new maximum length of 10,000 entries. The command returns the number of entries removed. In this case, we removed 20,001 of the oldest entries from the stream, leaving the newest 10,000. The second way to trim the oldest entries from the stream is to do so while adding a new entry with the xadd command. And this is the more common strategy. If we know that we always want to keep the check-in stream to a length of 10,000 or less, then we simply specify that on every call to xadd, like you see here. As you saw earlier, xadd returns the ID of the entry that was added, but doesn't tell us what the new length of the stream is. For that, we can use xlen. And we see that the stream has been capped to 10,000 entries, including the newly added one. There's a lot more to Redis Streams than what I've presented here. So if you're interested in learning more, you should check out Redis Streams, our free online course from Redis University. I know streams can seem like a fire hose of information, so thanks for sticking with me and fording this river together. Happy learning, and see you again soon.